CSIS 2430 is filmed before a live studio audience.
Take a look at just a brief overview of what we're going to cover today. It's just three things. We're going to start by doing some practice problems, which will be done off camera. So if you're watching the video, sorry you can miss out on that. Then we're going to get into Pascal's triangle, and then the binomial theorem, and that'll be it for the day. All right, let's learn about Pascal's triangle. First of all, let's figure out how do we build Pascal's triangle. All right, who's familiar with Pascal's triangle? Okay, most of us? Okay. Yeah, today you will know not everything, but a lot about it. There's a ton of crazy mathematical awesomeness in Pascal's triangle. So the way we start with the number 1 at the top. We're going to build a pyramid, right, a triangle. And then the next thing that we do is we go to our left ones and we go to our right ones, all right? And how many ways are there to get to that spot where that arrow is pointing on the left? Just one way, right? Just going from that 1 down there. And there's only one way to get to that arrow on the right. So we end up in these little blocks here, and there's only one path from the top one to the left or to the right. There's just one path. So 1, right? Make sense? Okay, now from where we're at, we're going to go left and right again, all right? How many paths are there to the green spot? There's only one. If you're starting at the top, there's only one way to get to that green spot. How many paths to that yellow spot? Also only one. Okay? Now the inner spot, though. Oh, my colors are off there. Well, yeah, we look at the inner spot. I got my slides switched around. That's okay, though. The inner spot, look at that dark blue line. That's one path to that inner spot, right? You see that? The light blue line is another path to that same exact position. So there are two spots, or two paths to that number 2 there. Make sense? So another way to look at this is you can actually, if you add up these 2 blocks here, you will get this number here. And in a minute, we're going to see that if I add up these 2 blocks, I'll get the number that goes here. And if I add up these 2 blocks, I'll get the number that goes here. And then if I add up those 2 blocks, I'm going to get the number that goes there. And that continues all the way down forever. Okay? That's the basic idea. Feeling okay so far? Pretty straightforward? All right. So I'm clearing out all those arrows there. And we see, again, that there's we're on the outer sides, there's always only one path to any of those given ones on the outside. Okay? But there are 3 paths to each of those 3s. Right? There's one path to that 3 right there. See that? There's another path right there. And there's a third path right there. That's the only 3, that's the only ways to get to that 3. Make sense? Now, you'll see that this is symmetric, and that exact same set of 3 paths is also over here to the other 3. Okay? And this pattern carries on all the way through the entire triangle. And notice what I said earlier about adding up any 2 squares, the one directly below it will be the total of that. You guys see that pattern happening there? Okay? So 10, for example, is a total of 4 and 6. Or 6 is a total of 3 and 3. 5 is a total of 4 plus 1, so on and so forth on down the line. Okay? Let's just go ahead and continue. I think I got this out, to 9. This triangle is infinite. It can go forever. And this pattern, that's how you build it. You can, and if you only remember the first 3 numbers in the 1, 1, 1, you can build this triangle from memory. It's not that hard. So big picture of what the triangle looks like. We feel okay about that? Now, what does it do? Why do we care? We're going to talk about that for the next hour. Okay? There's a lot of cool stuff in here. Here are some of the properties of Pascal's triangle. And we'll talk about each one of these. The sum of the rows, we'll talk about that. Prime numbers, the hockey stick, I don't know the hockey stick theorem or the hockey stick property, whatever. Triangle numbers, square numbers, points on a circle, magic 11s, the Fibonacci sequence, Sierpinski's triangle, combinatorics, binomial coefficients. All these things are things that are hidden, if you will, in Pascal's triangle. Okay. Some of the rows. Now, if we label these like we do in our computer world, that the first row is really the 0th row, right? And we start that way and we label 0 through 8. And I noticed I took off the bottom row that was on the previous slides that had 9 because I just needed some space here. But if we do this, the sum of the row will be equal to 2 to the whatever row power. So look on the right there. The first one, if you sum up, what's 2 to the 0? 1. There it is. What's 2 to the 1? It's 2. And if you sum up those two blocks, it's 2, right? What's 2 squared? 4, right? And what is that? Well, that's this plus this, right? And all the way down, so it's 2 to the n where n equals the row. Every row will be, so 2 to the 8th, whatever that is, I think that's 256, is, well, I know it's 256, duh, that's a big number in our world, yeah, 256, right? But that 2 to the 8th, which is the 8th row, 2 to that power will be the total if you sum up all those values in the row. It's a cool little property, right? All right, why 2, by the way? Yeah.
Is it because from each square it's a binary choice?
Yeah, it's just like, it's kind of like a binary tree, right? Where you, from every spot on the grid, you can only go left or right, right? All right, so next one, prime numbers. So here's a description of it. If the first element, notice when I say first, not the 0th element, but the first element in the row is prime, then all the numbers in that row are divisible by that prime number, all right? So in other words, take a look at the green rows are the ones that have the first element as prime. The big yellow numbers are the prime numbers. And remember, the first element, this is the 0th element, right? I'm not talking about that. I'm talking about the first element right here. That's the first element. And that's the first element. That's the first element. That's the first element. Follow? And those are prime numbers, right? Those are the only ones in the picture that are prime. Well, what that means is that everything in this row is divisible by 3. And everything in this row is divisible by 5, and you can see that this is true. And everything in this row is divisible by 7. See it? Now, some of these things are just fun. Like if you're like a math nerd, this is just fun stuff to look at. They all have applications somewhere in the world of math or computer science. A lot of them we're not going to necessarily use in this class, but I want you to be familiar with this because this triangle is crazy powerful. We talked earlier about using propositional logic to build circuits, right? Well, when propositional logic was a thing long before circuits ever were a thing. It wasn't until George Boole discovered, hey, I could apply this logic to circuits. And bam, next thing you know, we got Boolean algebra, and this is sort of the foundation of computer science, right? So these things that were invented, hundreds or even thousands of years ago, that are still have modern applications today that we haven't even dreamed of yet. So this stuff to me is just very fascinating, right? Okay, so let's move on to the next thing here. The hockey stick. This one's kind of fun. So starting on any edge, one of the ones on the outer left or outer right, draw a line diagonally like you see my red line there, and then at any point you want, cut downward. So you can see that I drew from 1 to 6 and I cut downward. The first square that I hit, which in this case is the 21 there, those black numbers will add up to 21. They sum to that number. This works everywhere on the grid. So if I decide to put sticks there, okay, 1, 2, 3, 4, oops, back up. 1, 2, 3, 4, I cut right, that adds up to 10. And again, I'm cutting down. You always cut down. So this one on the left here, that's going from 1 to 6 to 21 to 56, and as soon as anytime I wanted, I cut left or cut down, that 84 is the sum of those. 1, 5, 13, 35 sums up to 56. Anywhere on the grid, that will work. Okay, so to just prove that real quick, let's just pick a spot on the grid. So Josh, give me a starting point, any one of these or any one of these.
Let's go with the second row, or the first row, I guess.
Right here?
Yeah.
Okay, and you want to start over here or over here?
Left.
Start here? Okay, now I'm going to draw diagonally, and anytime you want me to, you say stop here. Stop on the 4?
Yeah.
So that's when I cut down, right? Well, 1 plus 2 plus 3 plus 4 equals 10, right? No matter what. If I would have gone one further to 5, then that would add up to 15, and that pattern holds everywhere, infinitely, through the whole triangle. Pretty cool, right? Triangle numbers. Triangle numbers, it has to do with the number of dots it would take to make a triangle, okay? This triangle would take 1 dot, and you'll see what I mean as I get bigger pictures here. This triangle takes 3 dots. That triangle would take 5 dots. See what I'm saying there? Okay? and so on down the line. What is the triangle number? It is 1 or 3, or it's the number of dots. Those are called triangle numbers. Here's the formal definition. The nth triangle is the triangle with n dots on a side. So take a look here. This is the first triangle. It has 1 dot on the side. This is the second triangle. It has 2 dots on the side, on any side, right? This is the third triangle. It has 1, 2, 3 dots on any given side. 1, 2, 3, 1, 2, 3. Follow? Fourth triangle has 4 dots on a side. 4 or 4 or 4. Make sense? Okay? Follow that idea? Yeah? So the nth triangle is the triangle with n dots on its side. Okay, so the first triangle, 1 dot, second triangle, 2. The nth triangle, this is our summation. Remember we talked about sequences and summations? This is a sequence that you sum up here. The nth triangle here is equal to the sum of, if we start with 1 and go to n, which is whatever number we're on, the first, the second, the third, the fourth, and you sum up the 1 plus 2 plus 3 plus 4, then that will be the value, that will be the triangle number. So in other words, let's go with, this is the third triangle. The nth triangle is the one with 3 dots, is the third triangle. And we're saying it is the sum of 1 plus 2 plus 3, which is 6. That's a triangle number. Dig it?
I dig Sugar Smacks.
Also, we should recognize that, right? Isn't that the same thing? That's our Gauss's formula for summing a number from 1 to x, right? 1 to n in this case. So that's what a triangle number is. What does that have to do with Pascal's triangle?
Good question. You should ask him that when we get there.
The triangle numbers are located in this darkened row here, this diagonal here. You can see that's 1, that's 3, that's 6, that's 10. Those, if you take those numbers, you can make a triangle out of them. Now, in a minute, we're going to look at square numbers. And square numbers, it's the same idea, where think about the number 4 squared. And if you were to make dots to make an actual physical square, what would that look like? It'd be 4 dots on any given side, wouldn't it? They are also here, in this same row, starting with the second row here, with the number 1, plus 3. 2 squared, the red number, is 1 plus 3, is 4. Follow? Okay, so that same diagonal row, and this is the second row, if you're going 0, 1, 2, it's always starting here, and it's always this diagonal here. We look at this number here, and it will be this first digit plus the next digit. So in other words, when I look at 3, that you'll notice is now highlighted in red, well, what's 3 squared? It's 3 plus 6, 9. What's 4 squared? 16. 5 squared, 25. You following? Okay? So on down the line. 6 squared is 36. 7 squared is 49, and we don't have any more to do, but that it would continue holding true. Okay, so how do we feel about that basic idea? And notice, I'm highlighting the number over here, right? But it's the first element, right? So wherever the first element is, make your way over to that one diagonal row, which is right here, and add up that and the next one, and that will give you the square. So if you had a really big triangle, and you wanted to square some number like, 319 or whatever, it'd be easy if you had the triangle. Now, it'd be a big triangle, right? But you just see it, and it'd be right there. All right. Questions about that? Points on a circle. Now, this one is just crazy. How they found this, I don't know. So we ignore the 0th row for this one. Here's the idea. The green diagonal, and it will be just that full diagonal row, the first number of each row, right? Not the 0th number, but the first number. That's the number of points I could put in a circle, put on a circle. And the number in blue directly next to it will be the number of lines that I draw. And the number next to that in red will be the number of triangles that will be formed. So here's what this means. If I drew 1 point, well, I can't even draw a line, right? Because it's 1 point, all right? So no triangles, obviously, and you don't see anything here, right? If I drew 2 points, I can draw 1 line, right? That is possible to draw a line. But there will still be no triangles that would be formed by the lines I drew, right? And we'll see a picture in a minute. If I drew 3 points, and I drew 3 lines connecting those points, there would be a single triangle in the diagram. And if I drew 4 points with 6 lines, there would end up being 4 triangles. let's watch and see. Looking at the first one here. 3 points, 3 lines, 1 triangle. See it? This one I have 4 points, that's the green number, 6 lines. You see all 6 lines? How many triangles we have? 4 triangles, right? But that will hold infinitely. It's the strangest thing, right? But it gets weirder. The blue line is how many quadrilaterals there will be. So in other words, if I had 4 points and I connected them with 6 lines, there would be 4 triangles and there would be 1 quadrilateral. What's a quadrilateral? 4-sided shape. Well, look back at that previous slide. Yeah, a square or a rectangle, and sure enough, there's 1 quadrilateral right there. But it gets crazier. But wait, there's more. That's the number of pentagons you'll have. That's the number of hexagons you'll have. That's the number of heptagons you'll have. Notice what's happening here. Triangle, yeah, somebody was really bored one day. Triangles, look, 3, 4, quad, 5, pent. We know these, right? 6, hex, 7 is hept, and 8 is octagon. I think I do have octagon on the next slide. But this, and so this number here would be how many octagons there were, right? So in other words, if I had 8 points and I drew 28 lines connecting them, there would be 56 triangles, 70 quadrilaterals, 56 pentagons, 28 hexagons, 8 heptagons, and 1 octagon. That would be in the pattern. This will just go infinitely, right? If you want to know how many 20-sided things there will be, you can figure out how many dots you'd have to draw and how many lines you'd have to use to connect it by getting to the 20th row in Pascal's triangle. Crazy. It's very cool.
Cool party.
All right, how do we feel about that one? It's one of my favorite properties, but there's more. There's still more. It's really strange. So, Magic 11s. This one is nuts too, all right? What is 11 to the 0th power? It's 1. What's 11 to the 1st power? It's 11. Yeah. What's 11 squared? It's 121. What's 11 cubed? It's 1,331. 11 to the 4th is 14,641. That continues infinitely. Now, when you get to numbers on the triangle that have double digits in each square, you have to, it's a little trickier to see it, but it's still there. So let's look at what's going on there. Okay? Would you agree that 14641 is the same thing as that? Then when we multiply that out, we get 10,000 plus 4,000 plus 600 plus 40 plus 1, which was that number that we just had a second ago, right? We all see that? That becomes that number when you add that all up. All right, well, let's look at the next row on the triangle. If we do 11 to the 5th, somebody do that on the calculator real quick. 161,051, okay? Remember that number. We'll come back, we'll be there in a minute. Now, look what we're doing with these numbers here. I'm just taking the blocks there and I'm putting what column they're in, right? There's the number you just said, right? We're just writing it on the board there. That's the number he just said it calculates to. But here's the thing. You can't have 10 hundreds, right? With the way we do math, that doesn't work in our system. You can't have 10 thousands, so you have to carry, right? These are our ones column, our tens column, our hundreds column, and so forth. We have 1 1, 5 tens, we have 10 hundreds, but again, that's not allowed. So what do? Carry the 1, right? Well, now we have 11 thousands. What do? Carry the 1. Now we have 6 10,000s, and we have 100,000, and there's your number. So if you can do that in your head, which isn't that hard, you can actually calculate any of these if you have the triangle in front of you. So, for example, I'm looking at this column right here, 1, 7, 21, 35. In the ones column, I have a 1, agreed? In the tens column, I have a 7, yeah? In the hundreds column, I can't have a 21, so I have a 1, carry the 2. Well, I carry the 2, I get a 37, right? But I can't have that, so I put the 7, carry the 3 over, now I have a 38, right? Can't have that, so I carry the 3 over, now I get a 24. Can't have that, so I carry the 2 over, giving me a 9, and then I have a 1 in the last column. That should be 11 to the 7th power. Calculating it? Assuming I didn't goof anything up.
It's accurate.
Yeah, got it? So that's not that hard to do in your head. If you have the triangle in front of you, right? Because we all carry that around in our pocket, right?
Is that testing legal?
If you can recreate it on paper, that's, you know, I mean, for me, everything's open book. But in some other scenario, if you're allowed to show your work, well, I showed my work. I recreated Pascal's triangle, which you can do if you just remember it starts with 1. That's all you have to do. Then you can build the triangle. So now we have, look, Fibonacci, okay? This is also in the triangle. What is the first couple numbers of Fibonacci? 1, 1, then what?
2.
Yep, 2, 3, 5, 8, right? Okay. So in order to see the Fibonacci, we got to make the triangle look a little different here. Same numbers, but we just have this closely drawn pattern. If I start with the first number, with the 1, and I draw a line diagonally from that 1 up to my right in that same diagonal angle, that is the first number of the sequence. If I go down to the next one, right, that's the first number of the sequence. If I go to that next one and I draw a diagonal, I'm crossing through only 1, right? I'm only crossing through 1 value there, okay? If I go to the next one, and I draw it, I'm crossing through a 1 and another 1. You see what I'm saying? I'm actually crossing right through the center of it. That's 2. If I go to the next one, I'm crossing through 1 and 2, which is 3. I'm crossing through 1, 3, then 1, which adds up to 5, and that is the next number of the sequence, 1, 4, 3, and so on down the line. That will just keep going infinitely. Now, you have to draw a perfect triangle here with the perfectly shaped, you know, what is that, 1, 2, 3, 4, 5, 6 septagons, right? And you have to make your angle perfect, right? But, or hexagons, I apologize. But you have to draw that perfectly to get that. That's a little trickier, but it's there. But wait, there's more.
I'm not done yet.
Sierpinski's triangle, you guys familiar with this? This is super cool. These are links in the PowerPoint. So if we go here to this one, Armstrong Academy.
To make a Sierpinski triangle, simply connect the midpoints of an equilateral triangle and then color in the upside down triangle in the middle. You can continue that pattern for each of the newly created triangles for as long as you like, or as long as you can keep fitting triangles in. The pattern goes on forever in both directions, thus making it a fractal.
So that's kind of cool, right? Well, take a look at this one. This is a longer video where he codes up a Sierpinski triangle, but he uses it, does it using randomness, and it's really cool if you put these certain constraints on the random location a dot can appear, the Sierpinski triangle will appear. This guy is one of my favorite channels, but you can see you can see the code here where he's already got it finished. But if we scroll up ahead here, I believe right around here, you can see these dots are being randomly generated and they're actually forming the triangle. But you can see that if he does it, lets it run long enough, the triangle will form. See it happening? So he builds this up in 2 videos. From this one's about 13 minutes, and this part 2 you can see on the right there is 16 minutes. This whole thing's about half an hour. It's worth a watch. In this case, he's using a JavaScript library called P5. It's pretty cool, but it's a cool little project. So it's just fun to look at, right? All right. Well, what does that have to do with our triangle here?
Good question.
Here is Pascal's triangle. If you color in all the odd numbers infinitely, it builds Sierpinski's triangle. That goes infinitely. I just ran out of space on the screen, but you could already see it there, right? It's happening, and it will happen infinitely. So many more things here, but this is a good start to get our head around how cool this triangle is, right? The next thing we're gonna look at here, I'm gonna pause the video, but there's a link there, so if you're not live here in the classroom, you can click on that link that says Galton Board, and you can see a video version of what I'm about to show you right now here in class. So why does this stuff matter? Well, this actually has a really cool application in combinatorics, right? And we're going to take a look at that right now. So 4, choose 0. How many ways are there to choose 0 things from 4? 1, right? This is a combination problem. Also combinatorics, because combinations and permutations and all that stuff is all under the umbrella of combinatorics. 4, choose 1. How many ways can I do that? 4 ways. 4, choose 2. If you remember the triangle, you can guess the next number. 1, 4, 6. 4 choose 3 is 4. 4 choose 1 is 1. Remember that number? That's row 4 of Pascal's triangle. And if I were to do 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, that's what I would get, are those numbers there. So this choose 0 through itself. 0, then 3 choose 1, 3 choose 2, 3 choose 3. Okay? 2 choose 1, 2 choose 2, 2 choose 0, 2 choose 1, 2 choose 2. 1 choose 0, 1 choose 1. That holds infinitely in the triangle.
To infinity and beyond!
Why is that interesting? Well, here's our fun thing that we love to do, which is raising binomials to a power, right? We know how to square this. That's not that hard. Just FOIL it out, right? And if you trust my math, which Amanda found a mistake in my this is why we're re-recording this, because in the video, the next thing said, trust me, the numbers are correct, and they weren't. I actually missed one spot, so I had to go back and fix it all. That's why we're re-recording. Thank you, Amanda. All right, so a plus b squared is that. This is the one that was wrong before, but now it's correct. That is the correct final answer, right? And let's just go, I'm going to say it again. Trust me, the numbers are correct, even though I've been wrong before, right? This is a plus b to the 4th power, right? What is a binomial anyway? What's that all about? Look at the etymology of the word binomial. What's bi mean? 2. Nomial? Number, right? It's somewhere it's rooted in number, right? So it means 2 numbers, 2 terms. Well, we have some number times a, that's 1 term. Maybe it's 3a plus 5b or whatever. That's the 2 terms, the a and the b, right? So these are binomials. If you're going to raise it to a power, this is the calculation. We're not going to go to the 5th power. This is good enough to prove the point. So would you agree that that top equation, a squared plus 2ab plus b squared, is the same thing as that new one right below it? Is that mathematically the same thing? Right, multiplying by 1 doesn't change anything. Adding the b to the 0th power doesn't change anything. It's still a 1. Then adding it to the 1 power on a and b doesn't change it. It's still just a. And then 1a to the 0 is just 1. Right? Okay, you agree with that? All right. Would you agree that that's the same? Last one, same thing. I made a few tweaks there in red. It should be correct. Okay? So now, question is, what is a coefficient and what are they in these equations? What is the coefficient? Not specifically to these, but just in general. What do we mean by that?
The number accompanying the variable?
It's the number right before the variable. So what are the coefficients in these final outcomes here? Look at the a squared, or the a plus b squared. The coefficients are 1, 2, and 1. Look familiar? Look at the coefficients for a cubed, or a plus b cubed. 1, 3, 3, 1. Look at the next one. 1, 4, 6, 4, 1. That holds infinitely on Pascal's triangle. So how do we use that? If you look at the triangle, you can see the coefficients there. And if I wanted to know a plus b to the 5th, that would be those numbers, which was 1, 5, 10, 10, 5. 1 would be the coefficients. So how do we calculate all this? Right? Now look at this. Look at the powers. A to the 4th, a to the 3rd, a squared, 1, 0. It starts at whatever I'm raising my power to, 4, and then it counts backwards, 3, 2, 1, 0. Then B goes the other way. 4, 3, 2, 1, 0. Right? Now with that, you can construct easily, if you have Pascal's triangle, a plus b to any power. All right, so we see this pattern that's happening here, right? Well, let's see what we can do with that. Notice that 1 is 4 choose 0, 4 is 4 choose 1, and so forth down the line, right? Okay, if that's the case, then could I not write the answer this way? I just replaced the numbers with the actual combination formula, the choose formula, right? So a plus b to the 4th is the same thing as 4 choose 0 times a to the 4th times b 0 plus 4 choose 1 times a cubed times b1 and so forth down the line. That's mathematically the same thing, agreed? All right, well, let's continue this. This is what's called the binomial theorem, which is how to calculate using the choose formula, and you can steal the numbers right off of Pascal's triangle. So here's the idea. I'm going to, let's do, for example, 3, right? If I want to figure out what the answer to a plus b cubed is, this is what I do. I start with 0, and I'm going to go to 3. And I sum up the total of 3, because that's what we're starting with, choose 0, times a to the n minus k. What's n minus k? Right now, 3 minus 0, which is just 3. So a to the third power, and then times b to the k, which is 0 at the moment, which is exactly that right there, right? Then I'm going to sum that up when I iterate. K is now equal to 1, and still 3, because that's always going to be 3. So now it's 1, so it's 3 choose 1, which we see that here, times a to the n minus k, 3 minus 1, which is 2, and you can see it there, times b to the k, which is 1, and you just keep doing that, and you'll sum it up, and you'll end up with that answer. So that little formula right there, and knowing Pascal's triangle, you can actually replace those combination questions there, the choose questions, with actual real numbers. Kooky stuff. Hopefully, mind blown. To the whiteboards. All right, we're back from the whiteboards, and I see that everybody got the idea here. I'm just going to put the answers on the board just so we can see it. But a plus b to the 7th, and I plugged in the actual numbers. Most of you put the combinatorics formula, 7 choose 1 or choose 0 and so on down the line. But if you looked at Pascal's triangle, this would be those values on the 7th row, right? The 1, 7, 21, so forth, right? And then the next one here, let me back up and show you what I did there. So I put in the numbers from Pascal's triangle, and I also have the b to the 0 and so forth. But when all is said and done, you evaluate that, you can get rid of all the anythings to the 0 power, because that's just 1. You can get rid of all the 1s, and this is the simplest form of that, okay? So if you ever see a question that's giving me the simplest form, this is what we're looking for here, okay? I don't think I have any questions like that for you, because it's pretty easy, and you guys get it here. So a to the 10th, I've already taken out all of the zeros, powers, and the number 1, and this is what the final formula will look like, okay? So I'll leave that up for a second for you guys to look at and just kind of compare what you wrote on the board. Hopefully you had the right idea. And hopefully I don't have any typos. That was hard to write those, man. Back to the whiteboards one last time before class is out, and see if you can answer these 4 questions here. Take the last 2 or 3 minutes here to look at how these work out, and I think I just showed the answers there. So this is, the first one is 11,440. If you did the math correctly, then you would have gotten that answer. What is the correct math? 16 choose 9 or? 16 choose 7. They're both the same thing. Yeah, they'll both be the exact same thing, right? And the next one, 12 choose 9 or 12 choose 3 will be 220, right? Look at the next one. That you probably discovered that's when you did the third one there, right? One of the cases you probably did 12 choose 3, and the other case you probably did 12 choose 9. You get the same results. Okay. The last one. How about that? You guys fell for it. That one doesn't exist, right? Right? It does not exist. Okay. Does no such thing. All right. So if you were to look at Pascal's triangle here, let me just see. Let me pull up real quick. I have one in a spreadsheet that's humongous. I just made a formula to calculate this down. So looking back here, if we were to look at this one, 3 and 9, right? We're looking for, and that was a total of 12. We're looking on the 12th row. We're looking right here, and we're looking at 12 choose 0, 1, 2, 3. Same thing with the 7 and the 9. I look at the 16th row here, and it's choose 0, 1, 2, 3, 4, 5, 6, 7. And that's your answer right there. Okay? Questions about anything we covered today?
Why does the fourth one not exist again?
Because, the question was, why does the fourth one not exist? Because what's 5 plus 7? 12. I'm raising this to the 11th power. So if I look here, there's no such thing. Where do I look? If I look on the 11th row here, there's never a case where you're going to have the 5th power and the 7th power at the same time. Remember, because you always count from up with the A's, you go A, it'll be to the 12th, or sorry, to the 11th and 10th and 9th and 8th and so forth. And then the B's are gonna go the other way. There'll never be a place where 5 and 7 are on the same coefficient, those two together. That make sense? Other questions?